So let us consider the Lagrangian of a point particle, and suppose that this Lagrangian only depends on positions and velocities to simplify the problem. And I'm going to construct something that for each possible trajectory of the system, of the particle, will give me a number. So it is functional, traditionally denoted by S, such that when I plug in some trajectory, whether it is one that satisfies the equations of motion or not, does not really matter, and gives me some real number. Okay. This S is defined as follows. It's the integral between 2 times of the Lagrangian evaluated on that particular trajectory. So I take the trajectory, I compute the derivatives of the xi's, I plug everything on the Lagrangian, and I take the integral with respect to time between t0 and t1, because when I evaluate the Lagrangian, everything depends only on t. This functional is called the action of the mechanical system. In this case, if it is a particle, it's the action of a particle. And the number that comes from here has dimensions of energy, because the Lagrangian has dimensions of energy. It's kinetic energy minus potential energy times time, and energy times time is the same as it has the same units of angular momentum. And these are units of action, and remember these are the units of h bar, okay, the Planck constant. Now that we have this object, this functional at our disposal, we can consider the following situation. We have 2 points in space, xi1, xi0, and we consider possible trajectories, possible generic trajectories that do not have to satisfy the equations of motion, which start at x0 at time t0 and end at x1 at time t1. So we just focus on trajectories such that xi of t0 gives x0i, and xi of t1 gives me x1 of I. Then I can compute the action for all those trajectories. It is a restricted set of all the possible trajectories of this system. And then the principle of least action tells me that the physical trajectory, the one that will be realized by the system, is the one that minimizes the action. Within this set, restricted set of trajectories. Okay, so how can we check this? In this simple setting, we just have to see that the trajectory that minimizes the action satisfies the Euler-Lagrange equations of motion. In order to do this, we have to characterize how a physical trajectory minimizes the action. If it minimizes the action, if x, suppose that xi is this minimum, and we perturb it, so we add something to it, but such that this xi plus delta I still satisfies these boundary conditions here. So suppose that between x0 and x1 the physical trajectory is something like this, we are adding some small perturbation x plus, so this would be x, and this would be x plus delta x. The endpoint would be the same, but x plus delta x would be slightly different from x. And clearly, if it is a minimum, the property of extrema is that if it is the extrema of S, in this case, x plus delta x will be approximately the same as x, S of x. It doesn't change much. This is the main property of extrema. So now this will be as if we expand it, okay, in terms of delta x, we find that this is s of x to the order at which we are working, and then what we can say is that delta s over delta x evaluated on the solution is 0. This gives me a set of equations which should coincide with the Euler-Lagrange equations, and this is what I have to find. So how do I compute this delta s over delta x? Well, I will compute delta of s. Okay, so what is delta of s? Is by definition is s evaluated at x plus delta x minus s evaluated at x. But in practice, you see this is some similar to taking derivatives. What I'm going to do is, well, you will see. This is how variations are taken in physics. Okay, and I will identify delta s, delta x as the term in this variation that is proportional to delta x. Okay, so let me just do this. Okay, so when I change slightly x, the limits of integration do not change, and t does not change either. So this remains the same, and I only have to see how L changes. Now these variations are similar to derivatives. So basically I use the chain rule. So the variation of L will be the partial derivative of L with respect to xi, and the times the variation of xi plus the partial derivative of L with respect to x dot I delta x dot I. Okay, and nothing else, because I have assumed that my Lagrangian does not depend on the t. Now, before I take the next step, you see that since this variation delta does not act on time, it will commute with derivatives of time. So I have delta x dot I, which is the same as delta of the derivative of t of xi, and this, at least for this particular kind of variation that only acts on xi, this is the same as this. Okay, using this partial result, I continue the calculation and I write the t Okay, maybe I should explain first why am I continuing this calculation, and I'm not just taking this term as the term which is proportional to delta x. I could say that this is just delta x with respect to xi, what I have to compute here. But the point is that this term, I don't know what it is. It should be something proportional to delta x in the end, plus I don't know what, we'll see. So this term could also contribute to delta S over delta X, and then I have to massage it a bit and keep computing. Okay. Now what I am going to do is to integrate this by parts. So this will be the derivative with respect to t of delta L delta x dot I delta xi minus the derivative with respect to t of partial L partial x dot I delta xi, and you already see another contribution, okay, to delta xi, to the coefficient of delta xi. Okay, so put everything together, minus the dt, and you start seeing the Euler-Lagrange equation appearing. Okay, so this part is proportional to delta xi, but there is still this piece here. Okay, and we cannot claim that this is delta S over delta X unless we know what this contribution is, because still it could be something proportional to delta xi. Okay, since this is an integral with respect to t, and this is a total derivative, we can integrate this part. Okay, this stays as it is. Okay, I'm not going to bother to copy it. Delta xi, and then we have now the integral of, we have to apply Barrow's rule, and this between t0 and t1. I haven't written the limits of integration, but it is assumed that they are t0 and t1. Okay, we are restricting ourselves to this kind of configurations, and the integration limits are between t0 and t1 by definition of action here above. Okay. Now, the main property of these delta xi's that I have to evaluate at t1 and t0 is that they vanish. Okay, in this drawing that I did before, you see that delta x can be different from 0. It's the difference between x plus delta x and x everywhere, but that at the origin and at x0 and at x1, delta x must vanish, because otherwise x plus delta x will not satisfy the boundary conditions. So delta xi at t0 and t1 is 0, and because of this term vanishes. I don't know what delta L over delta partial L with respect to x dot I is, but I know that delta xi vanishes at t1 and t0, which is the only term that appears here. And then I have something which is proportional to delta xi, and this is delta S over delta xi by definition. Okay, so I find that delta S or delta xi is given by the Euler-Lagrange equations of motion. Wow. For a moment, these are just the left-hand sides of the equations of motion, and the principle of least action tells me that this has to be 0 when I evaluate it on solutions, which proves that the principle of least action is equivalent to the Euler-Lagrange equations of motion. When they are satisfied, the trajectory that satisfies it extremizes the action, in particular delta S over delta xi is 0. So let us finish by making some important remarks. Okay, the first remark is that in this derivation, in showing that the principle of least action leads to the Euler-Lagrange equations of motion, it's crucial that these variations really vanish at the boundary of integration, which here is the points t0 and t1. It is also crucial that there are no terms of the form delta x dot I in this total derivative here. Okay, so there are no terms delta x dot I here, because otherwise we would have to impose boundary conditions to them as well in order to make this term vanish. If this term does not vanish, this boundary term does not vanish, we cannot identify really what delta s over delta xi is. So it is crucial that the boundary term vanishes. But if we impose too many boundary conditions, we just kill all the possible solutions, because you fix not only the positions at the beginning and the end of the trajectory, but also the speeds, and this really kills the problem. Another comment is that we could have considered Lagrangians that depend on higher derivatives of the variables. Okay, and in fact, if you do this, you see that okay, you will have at some point partial derivatives of, for instance, x double dot I and delta x double dot I. Okay, since deltas and total derivatives with respect to time commute, you find this. And now, in order to bring this to a form proportional to just delta xi, you have to integrate by part 2 times. Integrating by parts 2 times, you will get this d squared dt squared over this term dl delta double dot, partial L partial double dot xi. But each time you integrate by parts, you get a sign. So instead of a minus, like here, you will get a plus. Another thing is that, okay, in this case, it is unavoidable that you will get derivatives of delta xi in the total derivative. But this is a system of higher order and in these variables, and the initial or the boundary conditions have to be of higher order as well. Okay, so then it is allowed. You have to take all these into account. And these are the basics of the principle of least action, and now we want to put it to use.